Hi, I'm Ben-Yaakov. This presentation is entitled Ideal Rectifiers. Please note that the referenced and demonstrated commercial devices that I'm showing here are for educational purposes only. There is no endorsement or recommendation implied. Rectifiers or diodes are used in many applications. I'm showing here just two applications. One is an OR arrangement in which we have a number of sources, say power supplies or batteries, and we want to feed them in a redundant way, and in particular to feed the battery or power supply with the highest voltage to the load. So here we have the OR arrangement of the diodes, so that when, say, VB is the highest voltage, D2 will conduct and the other ones will be blocked. So this is one application, or a simple application. Applications that require high frequency operation are the switch mode converters, and here I'm showing a flyback converter in which I have the switcher, the magnetic element, and then we have the secondary side, and here's the diode we are talking about, which has to be turned on while the power is fed to the output, that is when the transistor is in the off position. So this diode has to be fast, has to be turned on and off at the rate at which this converter is running. Now, diodes have various characteristics, and I'm showing here just two important points. One is the voltage drop. Now, silicon diode, here silicon diode, have a voltage drop of, say, 0.7 to 1.5, depending on the whether they are fast or slow diodes. Fast diode would have a higher voltage drop. And here I have a silicon Schottky diode, which has a, say, 0.4, 0.5 voltage drop. I'm not showing the silicon carbide, which can be used up to high voltages, not like the silicon Schottky. The silicon Schottky is limited to, say, 100 volts. Silicon carbide can go up to a few hundred volts and above that, but the voltage drop will be even higher, will be like 2 volts and perhaps higher. So if I have a current flowing through the diode in the forward direction, and say the voltage of the diode is, say, 1 volt, say 100 amp current, I'm going to have 100 watts, which is a lot. Another important characteristic is the reverse recovery process here. I'm showing the forward current, and then we have the IDT as we expose the diode to a reverse voltage. The IDT depended on primarily on the external circuitry, and then the current will go negative up to a reverse peak current. Here we have some charge associated with this process, the QRR, and of course the charge times the voltage is energy. So depending on the switching rate, switching frequency, we're going to have a loss here. And then we have this TRR, which is the time it takes to the diode to recover. So these are key parameters that we have for the practical diode or rectifiers that we have to take into account in the various applications. Now, in order to combat the problem of the forward conduction and the losses associated with it, we can use the synchronous rectification scheme. And I'm showing here the synchronous buck converter, in which we have two transistors rather than a transistor and a diode. And when this upper transistor is conducting, we have the powering stage, current is flowing this direction. And then when this transistor is off, then without the transistor, the current will be flowing through the diode. These I'm showing are the internal inherent diodes of the power MOSFET transistor. So if there's only a diode here, there'll be a voltage drop and a power loss. And if, however, we have a transistor which is turned on while the upper one is off, then of course the voltage drop will depend on the RDS on the resistance of the transistor while it is in the on state, which could be lower, and I'll talk about it in a minute. Here we have an application. This is a Flyback Converter. Again, transistor switcher, and then we have here, instead of a diode, we have a transistor. So the purpose of this transistor is to be turned on as we feed energy to the output, and so that the voltage drop will be that of a RDS on. However, this arrangement requires extra control, either from the primary side, or perhaps we can get by with a auxiliary winding. Anyhow, we need a external control to turn on this transistor at the right time and to make sure that it is off otherwise. This is more complicated if we have an insulation here, isolated stage. Here it's simple because it's the same control, so this is just sort of the complementary, but here it becomes more complex. Now, the idea of a synchronous rectification is, of course, that we are replacing a diode with a transistor which is in the on stage, behaving like a resistor, RDS on. Now, obviously, in order for this scheme to be useful, you have to have the voltage drop on this resistor to be lower than the diode that you intended to use, so that they should be actually much lower than that. So RDS on has to be lower than this ratio. And if I take an example of 1 volt voltage drop on a diode and 50 amp, for example, just an example, I come up with a 20 milliohm, so I'll need a transistor of, say, 5 milliohm or even lower than that for 50 amp. Now, if the voltage involved, the reverse voltage on the transistor in the off position, off state, is low, then that's okay. But if we are talking about high voltages, then achieving 5 milliohm is not simple and perhaps not practical. So here comes the ideal rectifier. The idea of the ideal rectifier is very similar to the synchronous rectifier, except that it does not need an external control. We have again a transistor, but we have now a comparator that looks at the voltage across this device, and then when the voltage is in the forward polarity, that is here it's a little bit more positive in the anode than in the cathode side, then the driver will turn on the MOSFET, so that we are going to have here RDS on. And then when again this voltage drops and the voltage here approaches 0, or it's a little bit higher than the anode side, then the transistor is turned off. So it is very similar to the synchronous rectification scheme, except that it is self-contained, autonomous, does not need a control signal, so you don't have to carry, in the case of a isolated state, the signal from the primary side to the secondary side. So it's kind of convenient. Now the key issue, of course, is how fast is this arrangement to be useful in, say, switch mode application. So there are commercially available a number of units like this. This particular one is a slow one. It's not intended for switch mode converter. For our arrangement of power supply or power sources or batteries, it's okay. We have here, this is the transistor, this is the inherent diode that I'm showing. This is the unit here, the LM5050 from Texas Instruments, or actually originally from Linear Technology. And here we see that the two sides are sampled, and then the transistor is turned on when there is a current flowing in this direction, and when the voltage at the output is higher, or if there is an intention of a current to flow this direction, it'll be turned off. So here is a glimpse at the inner circuitry. This is, of course, a simplified schematics, We see here the differential amplifier. Looking at this side and then at this side, there is some hysteresis here involved, and then there is a gate drive. Now here a N-channel transistor is using a FET, N-channel FET. So when the transistor is on, we have the input and out and load side potential voltage about the same, because the difference is the voltage drop on the RDS on. So in order to turn on or to keep the transistor in the on state, you need the gate voltage to be higher than this line, and in this line as a matter of fact, but it has to be higher than the source terminal. So they do have here a 12-volt charge pump power supply that provide this voltage above this source line, keeping the transistor on. Now the question, of course, how fast is this device? Now here the manufacturer is showing a sequence in which you have a case in which there is a forward voltage, it's a 200 millivolt, could be higher, and then there is a flip or reversal of polarity to a negative voltage. Here the element is conducting, the diode is conducting, and since the gate is high, the transistor is conducting. Now as the voltage flips over, reaches this value, then the gate is supposed to be turned off. And this is the time it takes it to get to 1 volt, which I guess is, say, below the threshold voltage, gate voltage of the transistor. Now the question, of course, what is this time? And if I look here at from the table, I see that this time is 486 nanoseconds. Well, I don't know how they got this accurate number. Well, let's say it's a 0.5 microsecond approximately. Well, that's too slow for switch mode converter, because you wouldn't tolerate a 0.5 microsecond reverse current. But for application like the one showing here, in which we have power supply or batteries which are discharging slowly, and then maybe you like to replace one or the other, then this timing or this delay is really acceptable. So for this application, this is okay. However, there are commercially available units which are compatible with the requirement of a switch mode converter. For example, this MPS unit, MP6908, as shown here, is intended for a flyback. You can use it in a flyback. This is the secondary side of the flyback. Here is the transistor. This is the unit, again self-contained. There's no signal coming in. And again, the voltages are sensed, and then the transistor is turned on and off depending on the voltage across it. So here we see a sequence again in which here the element is blocking. This is the VDS voltage is high, so the transistor is, or the diode is not conducting. Here it starts to conduct, the voltage is reversing, and as we can see, when it reaches minus 86 millivolts, it's in the forward direction, the unit is actually triggered, and the gate voltage starts to rise, and it takes a certain time, certain delay until we get to the 2 volt, which is, say, the threshold voltage of the MOSFET, and then it goes all the way up to the gate voltage. Now there is a delay here, which is very good, a blanking delay in which nothing will happen. It will not reverse the situation. This is very good against spikes and parasitic oscillation, especially in DCM. I'll talk about it a little bit later. And then, of course, as the voltage is reversing, getting towards 0, and when it approaches minus 40 millivolt, the gate voltage starts to drop, and then when it hits the minus 3 millivolt, then it's supposed to be off, and then there's another delay between this minus 3 millivolt and the time it crosses this sort of threshold 2 volt point, and this is the turn off delay. So the key question is, of course, what are these delays, this turn on delay and this turn off delay? And here are here's the information from the datasheet, and we can see that the turn on delay is nominal typical 30 nanosecond up to 50 nanosecond, and the turn off delay is same order of magnitude, 25 nanosecond to 45. This is compatible with a fast diode, not very fast diode. There are diodes which are faster than that, but it's impressive. I mean, it's fast. So it is compatible with switch mode units, switch mode converters. The blanking is about 1 microsecond, which is again very nice. We'll talk about in a second. So here we have some typical waveform provided by the manufacturer in the datasheet. We have, this is the secondary side, this is the transistor, this is VDS of the transistor, this is the gate voltage, and you see very clean, nice waveform. Here is a 110 AC input, this is 36 watt, and for this particular flyback it's in the CCM, continuous current mode, while here, when the voltage is 220, it entered the DCM, and still we see very nice waveform. This is again the transistor, so when it's low, the transistor is conducting. It's like a short, no voltage on it is very low, and this is when it is non-conducting. There is a nice feature that this unit has, and that is a slew rate detector. Now this is important because in a DCM situation you have a lot of oscillation after the transistor is turned off, and therefore there might be some malfunction. And here actually we see that there is a false triggering of the gate, which is bad. You don't want this to happen. So they do have a slew rate detector. The idea is the following. The transistor, the primary transistor, when it's turned on and off, is causing a very fast transition. That is, the slew rate is very high because you turn on the transistor fast on and off. And the oscillation, which are dependent on the resonant frequency, have a slew rate which is slower than this slew rate. So you can actually distinguish between the two, and this is this slew rate detection or detector, which looks at the slew rate, and if the slew rate is not fast, it will not turn off the gate. So here we see a situation in which this feature was enabled. Here it's disabled, here it is enabled, and then detection is taking place, and therefore you don't see these false triggering of the gate, which is of course very nice. Now, the idea of ideal rectifier, especially the fast one, is fairly new, and one would expect, and I would expect, that we are going to see in the near future many more units, many more feature and protection against oscillation and spikes, etc. And this could be potentially a very useful element in many applications and in switch mode converter for replacing the controlled synchronous rectification schemes. I have not used it personally, but I'm sure that it's going to be used in the future, and I'm definitely going to use it and try it. And it is a potentially useful approach that would simplify systems by eliminating the need for a tight control of the synchronous rectifier. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it interesting, and perhaps it will be useful to you in the future. Thank you very much.